I'm sorry, there's a correction. When you differentiate log of 1 minus mu, we don't just get 1 over 1 minus mu, but we also have to differentiate this and we'll get a negative 1. So this is going to be negative 1 times this factor. So instead of this, we're going to have a negative sign here. So continuing with the derivation, after we equate the differential of the log of likelihood to 0, we are going to get xi times 1 minus mu minus, I have just distributed the summation to the two terms, and you know that this 1 minus mu and nu don't interfere with the summation, so we can take them outside. So I'm going to get 1 minus mu times sigma xi minus mu times sigma 1 minus xi, and this is equal to 0. So let us call sigma xi as P. If you recall, you would know that xi would be 1 if I obtained head on ith trial, or it would be 0 if I obtained tail on the ith trial. So sigma xi is nothing but the total number of heads that you have obtained from trial 1 until trial n, and sigma 1 minus xi would be the total number of tails that we obtained in the n trials. So let us call it by n minus p. So the summation becomes 1 minus mu times p minus mu times n minus p equals 0. Simplifying this further, we get mu equals p over n. So what this means is the maximum likelihood estimate of the mu, which is 1 for the random variable x, which is 1 when we get a head and 0 when we get a tail, is the total number of heads that we have obtained in the n trials over the n trials. It seems very intuitively correct. Just remember this result. We'll be looking at it later on, but this is the flavor of MLE. So in MLE, we use the data that we have already seen to estimate the parameters of the distribution from which we have sampled our variables. Now let us look at one more example, which is the Gaussian distribution. So I'm going to focus on one-dimensional Gaussian, but you can extend the results that we are going to see here to multi-dimensional Gaussians. The essence of MLE remains the same. As you might see after this example, that the way you apply MLE more or less remains the same, just that the distributions that we are drawing our samples from are different each time. So earlier we saw a Bernoulli trial, which is a discrete probability distribution, and now we are going to look at a continuous probability distribution, which is probability of x. We are going to have two parameters here, a mean and a variance sigma square. Remember that the mean that we are going to denote here is different from what we saw earlier on for the other distribution. And the mathematical expression that relates x with mu is so this is the parametric form of Gaussian distribution. Very crudely, a Gaussian distribution looks like this, where this is the mean and your sigma square would be approximately distributed like this. And your Gaussian distribution, as you can see, extends over the entire real axis. And for every single point on the x-axis, you can find the probability density. This is point xi. You can find out the probability density. Now again, let us assume that we have a sample set D of samples that you have already obtained from the Gaussian distribution, and let us denote it by x1 until xn. So we have n samples that we have already sampled from the Gaussian distribution, and our goal is to estimate the parameters mu and sigma squared. So like how we estimated the parameter mu in a Bernoulli distribution earlier on, now we are going to get a maximum likelihood estimation of mu and sigma square. So the first step in maximum likelihood estimation would be to write the likelihood function. So the likelihood function here is going to be, again, is going to be probability of getting D given mu and sigma squared. And this is going to be probability that we have obtained x1 until xn given mu and sigma squared. And we are going to assume that x1 until xn belong to IID. So what this would mean is that this would become a product of probability of xi given mu sigma squared. Like before, we are going to take the log of the likelihood function and we are going to convert the product into a summation. And we are going to equate the log of this function to 0, right? We want to, sorry, not the log of this function, but the derivative of the log of this function to 0. So once we have the log likelihood, we are going to do the derivative of log likelihood over the parameters, and we are going to set it to 0. So as you, if you want to recall, probability of xi given mu sigma squared is given as 1 by root 2 pi sigma multiplied by an exponential function like this, x minus mu the whole squared over sigma squared. So now what does the log likelihood become? is going to be xi minus mu the whole squared minus n over 2 log sigma squared minus n over 2 log of 2 pi. So you can see that if you take the logarithm of this function, you would end up with this for the summation. So now that we have this, as you know, we are going to take the derivative of the log likelihood and set it to 0. So first I'm going to differentiate with respect to mu and then find out mu ml. So when I differentiate this expression with respect to mu, I know that these two are going to go to 0 because they are not dependent on mu. So I'm going to get 2 times I equals 1 to n xi minus mu equals 0. So this simplifies to n mu equals sigma I equals 1 to n xi, or my mu ml is nothing but the average of all the xi's that I've obtained so far. Again, this seems intuitively very correct. So if I want to find out the mean of a distribution from which I have sampled a lot of samples, then I just take all the samples that I have and calculate the mean of those samples. What about the variance? So to just recall, we had the log likelihood function as so I'm now going to differentiate this with respect to sigma squared. I'll know that this term will go to 0 because it will not depend on sigma squared. And now, instead of having mu here, since I already know what mu ml is, I'm going to take this as mu ml. So this is going to be negative 1 over 2, and I have a sigma squared here, so I'm going to get sigma squared to the minus 2 into sigma I equals 1 to n xi minus mu ml the whole squared. And since I differentiated with respect to sigma squared, this negative sign is going to become a positive sign, and this term would become 1 over sigma squared, and I'm going to equate it to 0. So I'm going to cancel 1 sigma squared, and I'm going to get 1 over 2 sigma squared times this expression equals n over 2. Again, I'm going to cancel the 2 and take the sigma squared here, so I'm going to get sigma squared ml equals 1 over n sigma I equals 1 to n xi minus mu ml the whole squared. So this is the maximum likelihood estimate of my variance from the data that I have already obtained. So as you can see, you can apply this technique to many distributions. So you need not even have the assumption of IID, just that it simplifies the mathematical expressions that we obtain. So now that we have seen the maximum likelihood estimation technique for a Gaussian distribution and a Bernoulli distribution, let us just take a step back and then see, does it always work? So I asked you to keep the mu maximum likelihood estimation that we did for the Bernoulli distribution in your mind. To just recall, for a Bernoulli distribution that we saw earlier, the mu ml was obtained as P over N. So let us assume that we had a data where we got 1, 1 and 0. This would mean that I got the head in the first attempt, head in the second attempt and tail in the third attempt. So my mu ml for the fourth attempt, if I want to estimate the mu with which I am going to get a head, it is going to be P, which is sum of all the heads, total number of heads that I have obtained, which is going to be 2 over n. This seems logical, but what about 1, 1 and 1? In this case, I am going to get a mu ml of 1. Okay, and what if I had obtained 0, 0 and 0? I am going to get a mu ml of 0. So as you can see here, a minute variation could cause a greatly different estimation of my parameter. The reason why we have such a huge difference in our estimation is because the sample size is really small. So as you can see, by chance if I obtain 0 in the first toss, then my mu ml estimate for the second toss is going to be 0. Similarly, if I obtain the head in the first toss, then my mu ml estimation for the second toss is going to be 1. So what we can see from here is maximum likelihood estimation may not actually give you the right values of mu if you do not have enough samples. So this has given us one particular, one particular scenario in which your likelihood function may not work very clearly. So now that we have seen what MLE is and one case in which MLE does not work, I just like to tell you in general when MLE would be the best to use. So MLE is an estimation technique that works best when you have large number of data samples with you. And you know the probability distribution from which the data samples were sampled distribution well. So this is a very critical point. So we have actually overlooked this point in the explanation that I did. So what I mean by this second point is that, so I assumed that I obtained all the data points from a Bernoulli distribution in the first case and from a Gaussian distribution in the second case. But what if I had actually obtained my x's from some other distribution in the second case but assumed wrongly that it was a Gaussian distribution? So you would actually see that MLE might not work really well if you make a faulty judgment about the distribution from which you have sampled. So this is something that you have to be really careful about. and you also have to be careful that you have enough samples with which you can do the MLE estimation. And just remember that when I say that you know the probability distribution well, you should know the parametric form of the probability distribution. That's all we have for the maximum likelihood estimation. I hope you have enjoyed this particular session. If you want to look at more interesting lectures, please visit www.projectria.org. Thank you so much for your time.